All right, class. So in this part C, I guess, of the lecture, I want to.
I'm not sure I understand.
Serious, pay attention to me. I want to diverge from the sort of general formula I gave on the previous slide, which sort of told you how to do this in general and maybe not entirely practical because, well, how do you get... It's sometimes hard to break these system matrices down into individual uncertain components. And so this formula is a little bit hard to apply. So I want to sort of give a more general, I don't know, maybe more practical approach to taking a given state space system and modeling it as a feedback interconnection with these uncertain parameters. So this is sort of a general approach. Take this example or this approach from the paper here, which gives an introduction to uncertainty modeling. And the approach is to break the system representation down into these four matrices, or the four sort of parameters of the system, A, B, C, and D in state space. This is sort of the transfer function representation. This is the state space representation. And then take the uncertain parameters in those system matrices and then form little block diagrams within the block diagram, which then you can use to write down your LFT representation. So to isolate the uncertainties in each of these little parameter blocks, right? Because these parameter blocks are multiplication by the system matrices, and the system matrices have the uncertainty in them, and so we're going to do an LFT on these individual blocks. And that'll allow us to isolate the uncertainties, the delta M, delta C, delta K, and so forth. Right. So I'm not going to do this, although you could, right? You do the LFT on these parameters because we have such a simple system here that we're sort of modeling here. Which is that spring mass interconnection where I don't use the state variable transformation. Remember, we had y2 equals mx dot. I'm not going to do that because if we do it in this approach, we don't require any particular tricks for this to work. So what do we do? So what are we doing? We're writing down basically each of the individual signals involved in the state space representation in order to isolate the individual parameters which factor in there, right? And here we got there's a 1 over m parameter, remember, right? So when we write this down, we get x double dot equals 1 over m times c x dot plus kx. Well, actually, it's minus because you move them to the other side. F minus cx dot minus kx. Yeah. So here f is our input, and so this particular signal, we're going to here place it right there. Then we got the 1 over m operation, and that gives us our x double dot, right? That comes there. And then the relationship, of course, between x double dot and x is just integration. Right? Integrate once, integrate twice. And then we get this signal by taking f and subtracting from it k times x and c times x dot. Right? So this is our canonical form of the block diagram for a state space representation, where we've isolated the parameters 1 over m, c, and k. And of course, once you've done that, right, we can do the LFT on each of those parameters in isolation, right? We know how to do additive uncertainties. That's what we have on C and K, sorry. Right, additive uncertainties. And so we know how to represent these as an LFT. Right here they're going to the left, but actually in the block diagram they also went to the left. And we of course write things from the left to the right in order to get the equations. They become easier to write down. Right, so if we sort of plug in here, 0 C naught. Oh, sorry, right, that's K. 0 K naught, weighting factor here K, K naught. 0 C naught, weighting factor eta C. Right. So we get some equations, and of course we'll have to label these right here. This is going to be whatever this signal is here, whatever this signal is here. So we have to label those. So let's call give these names VC, VK, and we don't really have to label that one because that's coming in. But we should give this one a name. Let's call it I don't know. Let's call it G for now. It's a bad name. Sorry, I don't actually use that later on, but just to be careful. So that's VK, VC, and then coming in into VC, of course, we have X dot. Coming into K, we have X. And here, let's write the other. We need to give these labels here. We'll call that UC. We'll call it, no, actually, I think we give it the other name. Call it YC to come out, and oh, sorry, these are Ks. YK coming out and UK coming in, and we'll call this YC coming out and UK coming in, UC coming in. And then of course we have the, I don't know why this one's going the other direction. Oh, because on the block diagram it went the other direction, that's why. And this one, this was that weird signal G. This is X double dot, or since we'll just call it X2 dot. And then we got something coming out here, which is going to be YM. We'll call it something out going UM, right? So these are done, right? We know that those are the additive uncertainty representations. So we already gave that on a previous slide. We didn't, however, give the inverse additive uncertainties, which actually is a little bit more complicated. Because remember, we have to put it in this upper fractional transformation, which, if you remember, is, I believe, M22 plus M21 I minus delta M11, I believe. I apologize for getting these wrong. Inverse M12, right? So how do we deal with this stuff? Well, the 1 over delta thing is a pretty straightforward translation, but then we got this other delta here, and so let's make this actually just delta M. Delta M, that's our uncertainty. We got this extra delta M here, and that sort of complicates our stuff. So normally this M22 would be 0 here because we don't have a nominal term. But we actually have to have an M22 in order to get rid of this delta M here, unfortunately. So how do we do this? So actually what we do is we write this this term here is M22 I minus delta M M11 over I minus delta M111, right? So sort of an identity thing there. And then if we get the other bit over here, right? So let's take it over here, equal plus M21 delta M M12. And then you get I minus delta M M11 there, also on the denominator, right? And so the reason we have M22 here is to cancel out the bits which have delta here, because we don't want it appearing in the numerator. So we actually have to choose our matrices kind of carefully here. So in particular, if we choose M22 to be 1 over M naught here, right? So obviously M11 here is going to be a to m, or negative a to m, right? Because we want this to be over 1 plus delta m a to m. So m11, right? That's that term. And then we got the we have to choose the other bits over here. So we remember we want this to look like this. So we have a 1. The only thing we really need is a 1 over m naught multiplying it, right? So clearly the m12 is going to be 1 over m naught, because we want that to multiply. Right. So sorry, that's m11. So we've got that 1 over m naught here term, and so we want m22 minus delta m, minus m22 delta m a to m plus m21 delta m over m naught. We want this whole numerator here just to be equal to 1 over m naught, right? And so we can do that by judicious choice here, right? So basically we want this term to cancel that term, right? So we choose m22 here to be 1 over m naught, 1 over m naught, 1 over m naught, right? And then that appears there and that appears there. And then we choose this m21 here to be a to m, right? And if we do that, right, we can see that these terms are going to cancel out, right? This term is going to cancel out that term, and so these disappear, right? That cancels that. And then we're just left with the 1 over m naught term here on the numerator. So in the end, we get equal to what we want it to be, which is just m naught 1 plus a to m delta m. So it's a little bit complicated how we have to choose these things to make it so delta doesn't appear in the numerator. So it's a little bit complicated, but anyway, it's not that bad. So this choice of the feedback interconnection gives us a sort of 1 over multiplicative uncertainty. Right? So we then plug those into the block diagram where we've like labeled all of these signals. Remember, right? We have those new signals. This one was what we were calling G, but we're not really going to give it a label, so we'll just roll with it, I suppose. And then we've got our block diagram. We've got a bunch of equations. For every block, we have an equation. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8 equations, right? So we have 8 equations. Where are all those coming from? Well, we actually have one more equation. We have the output equation. So actually 9 equations. So obviously we have 9 equations. 3 of them are pretty easy, right? They're just these equations, 1, 2, 3, which relate U, M, U, K, and UC to Y, M, Y, K, and YC. So those are straightforward. 1, 2, 3 equations dealt with. So those are the uncertainty blocks. So not a big deal there. The other one's a little bit more complicated, right? So this is going to be x2 dot. This is x1 dot, so x1 is just x. And then so this block, right? That x1 dot equals wait, hold on a second. X1 dot equals x2. Okay, yeah, there we go. Sorry, we did so this is x2 dot, and that's equal to this block, right? So that one goes over there. This x1 dot equals x2 through integration is this, right? Yes. No. So this is x1, right? And so x1 dot is equal to x2. Okay, yes. That's that equation right there. Right. And x2 double dot, right, that's this equation, right, is equal to, remember this this was a to m 1 over m naught, 1 over m naught, I believe, right? Previous equation. Yep. And negative signs, of course. Right, so x2 dot here, right, that's x2 dot, equals negative a to m times plus 1 over m naught times the signal which we labeled g earlier, g. Right, I guess that gives us another equation. So g is w minus vc minus vk, but that's okay. Then we have equations for vc and vk, right? Again, given by these blocks, which I believe were c naught, c naught. What was that? C naught a to c. A to c. So vc is a to c times u. And plus c naught times this signal, which is x2. Okay. x1 dot equals x2, so that's that. Finally, we've got this equation for vk, right? And again, right, that feedback interconnection 0 c naught or k naught, sorry, k naught a to k, right? So we got here vk equals a to k times uk plus k naught times x1, right? So that's that equation. It goes there. Let's see, this one goes here. And then what else do we have here, right? We have the outputs from each of these blocks. So ym, right, is given, where's ym? There, right? So that's those blocks, a to m, plus 1 over m times this this g thing there as well. And then we've got the other two blocks, right? They're pretty easy. yc, yk. yc is just c naught times x, and yk is just k naught times x1, right? So a bunch of equations, 1, 2, 3, 4, 5, 6, 7, and then we got these extra 3 for the uncertainty block, right? So we write down those actually, we eliminate this equation by plugging it in there. We eliminate this equation by plugging in here and here, of course. Right. And so we write down all these, right? Here's our first equation. Maybe I need a new color. Right, that goes there. x1 dot is just x2. x2 dot, right, comes down here. That's... well, we've got a bunch of terms here. The easiest one is a to m times and then we got these 1 over m's times these some g. Well, g, what is g? G is, well, 1 over m times w. That's the easy bit. 1 over m times w. There's that. And then we got these other three things. Sorry, other two things. So vc and vk, right? So those have their own equations. Right, so vc and vk. So vc is a to c times uc. Right, there's uc. So there's a to c times uc, but there's a 1 over m term in front of it, so that's that as well. And then we have the vk. There's an a to k times uk, so that's those two terms right there. And again, there's a 1 over m term in front of them. And then the other bits, right, from those two terms, right, the c naught and the k naught, right, they both bit multiplied by 1 over m. Their states, though, x1 and x2. So there's x1 and there's x2. Both have the 1 over m terms. Fortunately, our expression for ym is more or less the same. It's in fact exactly the same, at least for the second bit. Right. So that term just translates straight down there. That term translates there, straight down, straight down. In fact, the only term, actually, they all do, right? The a to m is exactly the same term as well. So the expression for x2 dot and ym are exactly identical, and so they just repeat. What else are we missing? yc, that's just c naught times x2. Yk, that's just k naught times x1. Lastly, we just have our regulated output, which is z, and that's just x1. Z equals just x1 right there. Right? So we have all these equations. We've now put them in state space form. These are the outputs which go to the uncertainty block, right? So if we were thinking in our previous terms, this was, I believe it, we were labeling this P, and that's P there. Actually, I forget what we were labeling it. Yes, P is the output, sorry. Right, yes. So P is the output, and then the output from the uncertainty block was Q. So these terms would be Q in our fractional transformation. Right. And then we got the regulated output and the exogenous disturbance there as well. So again, right, it's fairly complicated, right? You write down your block diagram, you have to do LFTs on each of these individual terms. But it's at least methodical, right? So you can you know you can do it. It's just a lot of bookkeeping. And I think there's a homework problem that also deals with a lot of bookkeeping. So have fun with that. So finally, we've put ourselves into the linear fractional transformation, given a couple ways of doing it. The easiest or most reliable is just to draw the block diagram and write down all the signals, right? P, Q, W, Z. So in the next lecture, we'll talk about what to do with this LFT. In particular, we have this annoying fact that our parameter structure is diagonal. And that's going to prevent us from straightforward application of things like the small gain theorem. So we know that each of those parameters has norm less than 1 because we use the weighting factor. And we know, of course, that the whole matrix, delta, has norm less than 1. But it also has structure. It has a diagonal structure. And so we have to somehow exploit that. And we're going to have to come back to that and work with that a little bit in a later lecture. And actually, this is that structural property of the uncertainty is actually a big unsolved problem, the structured singular value, a big unsolved problem in robust control. But we'll come back to that. And we don't have to worry too much about it at this point. Okay. So I'm going to stop this sort of little tutorial on modeling the LFT, and then I'll come back and give some other sources of uncertainty, such as nonlinearity and higher order dynamics and stuff, and talk a little bit about how to deal with those, but again, not in any great depth because they're a little bit beyond the scope of what we're going to be talking about.